It's a simple question. Why do we walk on two legs? Most animals don't. Our closest relatives, chimpanzees and gorillas, get around on four limbs. It seems like a strange thing for an ape to do, but this one change, this shift from four legs to two, might be the most important thing that ever happened in our history. Well, it's the event that kicked off everything else. It's the reason you're reading this right now. The answer isn't simple. There's no single reason scientists can point to and say, that's it. That's why we stood up. Instead, it's a detective story with clues scattered across millions of years. The clues are old bones, ancient climates, and basic physics. And by looking at them, we can piece together a pretty good story. A story about how a group of apes in Africa made a risky evolutionary bet that paid off in a huge way. To understand why it happened, we have to go back in time, way back. Think 6 or 7 million years ago. The world was different then. Africa, where our story begins, wasn't exactly like it is today. Much of it was covered in dense, continuous forest. For an ape living in that world, life was in the trees. Food was there. Safety was there. You could swing from branch to branch, moving through a three-dimensional world. Getting around on all fours, with long arms for climbing and grasping feet, made perfect sense. It was the ideal design for that environment. But then the world started to change. The climate got cooler and drier. It happened slowly over millions of years, but the effect was huge. Those vast, unbroken forests began to shrink. They broke apart. In their place, open spaces started to appear. Patches of grassland dotted with clumps of trees. This new landscape is what we often call the savanna, or woodland savanna. This change in scenery was a massive problem for our ancestors. The old way of life was becoming obsolete. The resources, the fruit, the leaves, the safe places to sleep were no longer connected by a canopy of trees. Now, they were spread out. To get from one patch of forest to another, you had to cross open, dangerous ground. The ground was where the predators were. The ground was exposed. The old body plan, perfectly suited for the trees, was suddenly clumsy and vulnerable out in the open. Something had to give. Evolution doesn't have a plan, but it responds to pressure. And the pressure was on. This changing world is the stage on which the drama of bipedalism played out. And it's what gave rise to the first and most famous theory about why we stood up, the savanna hypothesis. The idea is simple and intuitive. Imagine you're one of our early ancestors, maybe 4 feet tall, out on that new open landscape. The grass is tall. Predators like big cats could be hiding anywhere. If you're down on all fours, you can't see anything. Your world is a wall of grass, but if you stand up, even for a moment, you can see over it. You can spot danger from farther away. You can also see your goal, that next patch of trees with ripe fruit. Standing up becomes a survival tool. Over time, those individuals who were better at standing and walking upright were more likely to survive, find food, and have babies. So the trait gets passed on. For a long time, this was the standard explanation. It makes a lot of sense. It connects the environmental change directly to a behavioral advantage. But like many simple stories, it has some problems. When we look at the fossil record, we find that the earliest evidence for bipedalism in creatures like Ardipithecus ramidus dates back to over 4 million years ago. And the clues suggest Ardi lived in a woodland environment, not a wide-open savanna. The big grasslands hadn't really taken over yet, so our ancestors were already starting to walk on two legs before the savanna became the dominant landscape. That means seeing over the grass probably wasn't the initial trigger. It might have become an advantage later, but it doesn't seem to be the origin story. So, if it wasn't about peeking over the grass, what else could it be? This is where the story gets more interesting with more competing ideas. One of the most powerful theories has to do with something much more fundamental: our hands. Think about a chimpanzee. When it walks on the ground, it knuckle walks. Its hands are being used as feet. They're tied up, occupied with the simple act of moving around. Now, what happens when you stand up? Your hands are free. Suddenly, you have two limbs that are no longer needed for locomotion. They can do other things. And this is a very big deal. This is the basis of the carrying hypothesis. The idea is that the biggest advantage of walking on two legs wasn't about moving, but about carrying. What would you carry? Food is the obvious answer. In a world where resources are scattered, finding a big score of fruit or nuts is great. But you can't eat it all at once. If you're on all fours, how do you take it with you? You can't. You have to stay put, which might be dangerous, or try to stuff your mouth. But if you can walk on two legs, you can gather up armfuls of food and carry it back to a safer place, or back to your family. This idea of carrying food back to share is really important. It suggests a change in social structure. The male could go out, forage, and bring food back to a female and her dependent offspring. This is called provisioning. It allows the female to have more babies closer together because she has help feeding them. It strengthens the bond between males and females. It lays the groundwork for the family structures we see today. Freeing the hands to carry food wasn't just a practical advantage, it might have been the start of a whole new way of living together. And it wasn't just food, you could carry tools. At first, maybe just a useful rock or a sharp stick. Later, you could carry tools that you had made yourself. You could also carry your babies. Apes cling to their mother's fur, but as we became less hairy, that became harder. Being able to hold an infant in your arms while you walk is a huge advantage for a mother. So the need to carry things, food, tools, infants, could have been a powerful driver for evolving an upright posture. Then there's an idea that seems a bit strange at first, but it's grounded in basic physics. It's the thermoregulation hypothesis. In other words, we stood up to stay cool. The African savanna, even the early mosaic version, was hot. The sun beats down relentlessly at midday. For any animal, overheating is a serious danger. When you're on all fours, you have a lot of your body exposed to the direct overhead sun. Your whole back is a target. But when you stand up, you present a much smaller target to the most intense direct sunlight at noon. Only your head and shoulders get the full blast, the rest of your body is presenting a narrow edge. It's the difference between laying a book flat in the sun versus standing it on its edge. The edge absorbs much less heat. There's more to it than that. Standing up also lifts your body higher off the ground. The ground itself radiates a lot of heat. By standing, you get your torso and head up into slightly cooler, breezier air. More of your body surface is exposed to the wind, which helps with cooling through sweat evaporation. So, an upright hominin could forage for longer during the hottest parts of the day, when many predators would be resting in the shade. It would give them a unique niche, a time slot to find food with less competition and less risk. This radiator theory is a compelling argument because it's not just a guess, it's based on the physical laws of heat and energy. While these theories are the main contenders, there are others too. One less mainstream but fascinating idea is the aquatic ape hypothesis. This theory suggests that our ancestors went through a phase where they spent a lot of time in or around water. Wading in shallow water to find food like shellfish or water lilies would naturally favor an upright posture. It's easier to keep your head above water if you're standing. This could also explain other human traits, like our relative lack of body hair and a layer of subcutaneous fat, which is different from other apes. Most scientists don't support this theory. The fossil evidence just doesn't point to our ancestors living an aquatic or semi-aquatic life. But it's a good example of how people have tried to think outside the box to solve this puzzle. Another, more practical idea is the energy efficiency hypothesis. It's not as dramatic, but it's very important. The new landscape meant our ancestors had to travel longer distances between food sources. So they needed to be efficient walkers. It turns out that for a primate, walking on 2 legs over a long distance is more energetically efficient than knuckle walking on 4. A chimp can outrun a human in a short sprint, but a human can walk for miles and miles without getting as tired. Our bipedal stride, with its long legs and swinging motion, is a masterpiece of efficient movement. In a world where calories were hard to come by, saving energy on the commute between meals was a huge survival advantage. Every bit of energy saved on travel was energy you could put towards survival, growth, and reproduction. This theory ties in nicely with the others. We needed to cross open ground, carrying things and keeping cool, and doing it efficiently was the key. So it was probably not one single thing. It was likely a combination of pressures. A feedback loop. Maybe an ancestor stood up briefly to grab fruit from a low branch, something we see chimps do today. This is called postural feeding. Maybe that small advantage made them slightly better at standing. Then they found that standing also let them see over the grass, and their hands were free to carry the fruit they just picked. And while they were walking back, they were staying cooler and using less energy. One advantage bled into the next. Each small benefit of being a little more upright reinforced the others, pushing our lineage down a path from which there was no return. This change didn't happen overnight. It was a messy, gradual process over millions of years, with many intermediate species, some more successful than others. And it required a radical redesign of our entire skeleton. The transition from a body built for climbing to one built for walking was a massive engineering project, courtesy of natural selection. Let's start from the top. Your skull. In an ape, the hole where the spinal cord connects to the skull, the foramen magnum, is at the back. This makes sense for an animal that is leaning forward or on all fours. Their head juts forward from the spine. But In humans, that hole has moved to the center, directly underneath the skull. This allows the head to balance on top of the spinal column without needing huge, powerful neck muscles to hold it up. Finding a skull with a forward position frame and magnum is one of the clearest signs that a fossil species was bipedal. Then there's the spine itself. An ape's spine is relatively straight and stiff. It acts like a rigid bridge between their front and back legs. Our spine is different. It has an S shape, there's a curve in the neck, another one jutting out at the chest, and a big one curving inward at the lower back, the lumbar curve. This S shape acts like a spring. It absorbs the shock of walking and helps keep us balanced, positioning our center of gravity directly over our feet. The pelvis is where some of the biggest changes happened. A chimp's pelvis is long and narrow. Ours is short, broad, and bowl-shaped. This new shape provides support for our internal organs, which would otherwise slump down due to gravity. It also provides a wide base for the powerful gluteal muscles, our butt muscles, to attach. In apes, these muscles are mostly for climbing. In humans, they are massive because they are essential for keeping our torso upright and stable with every step we take. Our gluteus maximus is a uniquely human feature, a direct result of walking on two legs. Our legs got longer and stronger, and they changed their angle. Look at an ape's legs. They go straight down from the hips. Our thigh bones, the femurs, angle inwards from the hip to the knee. This is called a valgus knee. It looks like we're slightly knock-kneed. This angle is crucial because it brings our knees and feet directly under our body's center of gravity. It allows us to shift our weight from one foot to the other as we walk without lurching from side to side like a chimp does when it tries to walk upright. And finally, our feet. An ape's foot is basically another hand. It has a long, opposable, big toe, perfect for grasping branches. Our feet are completely different. They are rigid platforms designed to bear our full body weight. The big toe is large, in line with the other toes, and provides the final push-off in our stride. We've also developed arches, one running from front to back and another across the middle. These arches act like shock absorbers, cushioning the impact of each step and storing energy like a spring to help propel us forward. We lost the ability to grasp with our feet, but we gained a foundation for walking and running across the entire planet. This anatomical overhaul was a series of trade-offs. Evolution isn't about creating perfection, it's about finding solutions that are good enough to work. And our bipedal skeleton, while amazing, is full of compromises. The S-shaped spine that's so good for balance is also prone to lower back pain. Our feet bearing so much weight are susceptible to problems like flat feet and plantar fasciitis. And the biggest trade-off of all happened at the pelvis. The change to a short, bowl-shaped pelvis, so essential for walking, created a problem. It narrowed the birth canal. At the same time, another major trend in human evolution was happening. Our brains were getting bigger. This created a terrible evolutionary dilemma. We needed a narrow pelvis to walk efficiently, but a wide pelvis to give birth to big-brained babies. The solution was another set of compromises. Human babies are born relatively premature, altricial, compared to other primates. Their brains are much less developed at birth. A newborn foal can stand and walk within an hour. A newborn human is a helpless blob. This is because if a human baby stayed in the womb any longer, its head would be too big to fit through the mother's pelvis. This led to a uniquely long period of infant dependency. Human children need years and years of care. This, in turn, had profound social consequences. A mother burdened with a helpless infant for years couldn't do it all on her own. She needed help. She needed a supportive partner to provide food and protection. She needed a social group, a family, a tribe. Our difficult childbirth and long childhood may have been the primary driver for creating the complex social bonds and cooperative societies that define humanity. We needed each other to survive the consequences of walking upright. So bipedalism wasn't just a new way to get around. It was the first domino. It set in motion a cascade of other changes that ultimately made us who we are. The most significant consequence, without a doubt, was freeing the hands. Once our hands were no longer needed for walking, they were free to specialize. They became our primary interface with the world. We could carry things, we could gesture, and most importantly, we could make and use tools. Other animals use tools, and a chimp might use a stick to fish for termites. But no other animal has taken tool use to the extreme that we have. The first stone tools, simple choppers and flakes, appear in the archaeological record around 3.3 million years ago. They are crude, but they represent a monumental leap. With a sharp stone flake, an early hominin could do things its body couldn't. It could butcher a carcass left by a predator, getting access to meat and marrow high energy, brain-building foods that were previously out of reach. It could sharpen a stick to dig for roots or defend itself. This started another powerful feedback loop. Free hands led to tool use. Tool use led to a better diet, particularly more protein and fat. A better diet provided the fuel for a larger, more energy-hungry brain. A larger brain, in turn, could figure out how to make better, more sophisticated tools. Better tools led to an even better diet, which fueled an even bigger brain. Bipedalism didn't directly cause big brains, but it opened the door. It was the necessary first step that made everything else possible. Walking upright also changed how we saw the world, quite literally. Our main sense became vision rather than smell, which is more important for animals closer to the ground. It changed our vocal abilities. The way our skull balanced on our spine, along with changes in the throat, eventually allowed for the complex sounds of speech. So, when we ask why we started walking on two legs, we're really asking what was the spark that started the fire of human evolution. The environment changed, forcing our ancestors out of their comfort zone. A combination of factors to say the need to carry things, to stay cool, to move efficiently, to see farther made standing up a good bet. It wasn't a perfect solution, it came with costs like back pain and dangerous childbirth. But the benefits were immense. It was a gamble. For millions of years, our bipedal ancestors were not the top of the food chain. They were relatively small, slow, and defenseless in a world of powerful predators. But they had their free hands, their budding intelligence, and their growing social cooperation. They had a new way of moving through the world, and that new perspective changed everything. The story isn't over. We're still trying to pin down the exact sequence of events. New fossil finds can change our understanding overnight, but the broad outlines are clear. We are the apes who stood up. It was an awkward, difficult transition, a series of compromises written into our very bones. But by rising from all fours, we lifted our eyes to the horizon. We freed our hands to shape the world. And we took the first shuffling step on the long, improbable journey to becoming human.